Okay, let's start with Ohm's law. So the statement of the Ohm's law is at a fixed temperature, the current flowing through a conductor is directly proportional to the potential difference between 2 points of the conductor and inversely proportional to its resistance. So in mathematical terms, that would be I is proportional to V and I is inversely proportional to resistance. Now we combine these two proportionalities, and we write an equation, a formula. I is equal to V over R, and this is the Ohm's law formula, and it's a very important formula for electricity. Now let's move on to electrical circuits. Now, what is an electric circuit? An electric circuit is a complete path of the flow of electricity. So an electric circuit would consist of a source, which can be any source, AC or DC, battery or generator, whatever, and then that would be connected to a load. It can be one load or many loads. We're just drawing a basic circuit here, so we're considering only one load, and the complete closed path for the flow of electricity. So this was our load V, and this was our resistance R, or load. Sorry, this was our source V, and this will be our load R, and this path is the complete conductive pathway. Now, electrical circuits are of three types. So there are one series circuits, there's two parallel circuits, and there's three mixed circuits, also known as series parallel circuits. Series parallel. Now let's explore what series circuits are. So in series circuits, all the loads are connected in series. So say this is our first load, then we'll have another load. Let's draw another one, and let's term them R1, R2, and R3. Now, as a series circuit, all the loads are connected in series, so end to end, one after the other. And this would be the source. Let's complete the circuit. So this is the source, and here's the complete closed conductive pathway. Now, as you can see, each resistor or each load is connected end to end. And if you consider that these are the two endpoints of R1, and again this would be the two endpoints of R2, and again this would be the two endpoints of R3, then notice that every two resistor, so R1 and R2, has a single endpoint in common, single endpoint connected together. Again, R2 and R3 has this one single endpoint connected together. So this is an important identifying factor or feature of series circuits, that every two resistor in a series circuit has a single endpoint connected together, or single common endpoint. Now the total resistance in a series circuit would be, total or equivalent resistance is RT is equal to R1 plus R2 plus R3 plus ... plus Rn. So the total or equivalent resistance in a series circuit is the sum of all the individual resistances. And another important feature of series circuits is that in a series circuit, the current flowing through all loads is the same. So again, if we have R1, R2, and R3, R1, R2, and R3, there would be a single current flowing through all of them, a single current I. Okay, there would be no individual I1 or individual I2 or individual I3. The same current flows through all of them, but there would be individual voltages. So R1 would have an individual V1, R2 would have a different V2, R3 would have a different V3, where V1 would not be equal to V2, would not be equal to V3. Yeah. So in a series circuit, the voltage around each resistor is different, but the current flowing through each resistor is the same. Now let's move on to parallel circuits. Now in a parallel circuit, each load is connected in a different branch. So if we have R1 here, then say we had R2 and R3. These are all separate branches. So each resistor would be in a separate branch, and then completing the circuit, this would be the source. Okay. Now we have the source and 3 resistances and a complete conductive pathway. And this would be R1, R2, and R3. Now as you can see, each resistor is an individual branch in itself. They're not connected end to end, not connected in a series. They're connected in separate branches altogether. And again, considering the endpoints of each resistor, so the endpoints, now we have the differentiating factor between series and parallel circuits, that in parallel circuits, every 2 resistor has 2 endpoints connected together, so 2 common endpoints. Again here, 2 common endpoints. Now remember, in series, each resistor had a single common endpoint, but in parallel, every 2 resistor has 2 common endpoints. So that's the differentiating factor between series and parallel circuits, and an easy way to identify which circuit it is. Now the total resistance or equivalent resistance in a series circuit is calculated in slightly differently than total resistance in a parallel circuit is calculated slightly differently from series circuits. Now it's calculated like this. So 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... 1 over Rn plus 1 over Rn. Okay. Now this can be written even more simply as such. So RT is equal to R1, 1 over R1, 1 over R1 plus 1 over R2 plus 1 over R3 plus ... 1 over R1, R3, 1 over Rn, and then we enclose them in brackets and to the power minus 1, so invert them all. That's how you find the equivalent resistance in a parallel circuit. Now again, another important feature of parallel circuits is, let's draw 3 branches again. Okay, so the voltage through, again let's turn them R1, R2 and R3. Now the voltage through each of them would be the same, so there will be just a single V voltage for all of them. Single V here, V here, V here, it's all the same. There will be no V1, V2 or V3, they will all be the same. However, so the voltage through each resistor in a parallel circuit would be the same. However, the current flowing through each of them would be different. So there would be an I1 here, there would be an I2 here, and there would be an I3 here. And each of them would be different. So I1 would not be equal to I2, would not be equal to I3. Considering that if R1, R2 and R3 would be different. So that's another differentiating factor between series and parallel, that in series circuits the voltage is different but current is same. However, in parallel circuits the voltage is same but current is different. Now let's move on to mixed circuits or series parallel. In series parallel circuits are basically the combination of series and parallel connections. So they have no special law or anything, just the combination. So we could have series connection here, then parallel connection again parallel connection, again series, etc, etc. So as you can see, this is in series. However, these two are in parallel. Again, this is in series, so it's a mixed circuit, mixed connection. Now let's move on to some practice questions. So this is a series circuit question. As you can see, R1 and R2 again has one common point, R2 and R3 has one common point, R3 R4 has one common point, so we can determine that this is a series circuit. Now we have to find IT. Now how do we find IT? Let's change the color to green. Okay, so we find IT. I is equal to, from the Ohm's law, so V over RT. Now here voltage and electromotive force E is given here. Although electromotive force and voltage has some differences, for the sake of calculation we can consider them to be the same. So V and E are the same, and down here we have RT. Now let's find RT. So for RT, from the formula that we had, RT is equal to R1 plus R2 plus R3, and we have here R4 plus R4. Let's substitute the values. So we have 2 kilo ohms here, so 2 kilo ohm plus 3 kilo ohm, 2k plus 3k plus we have 4 kilo ohms, 4k plus 5k, 5 kilo ohms. In total we have, so that's 5 plus 9, so 14 kilo ohms. 14 kilo ohms. Now putting that the value of E is equal to 20 volts, so 20 over RT is 14 kilo ohms. So kilo ohms means 14 times 10 to the power 3, equal to, we have 20 over 14 into 10 to the power 3, 1.43 milliamperes. 1.43 milliamperes. That is our answer. That's IT. You can put IT here. Now let's move to the next question. So we have another series circuit question. R1 and R2 again has a single common point, so they're in series. However, notice that this doesn't have a complete connection down here. You might think it's not connected, but actually here there's grounding and here again grounding, so they are indeed connected, but through the earth. Yeah. Now let's see, again the formula would be I is equal to, we have to find IT, so I is equal to V, or in this case E, over RT. Now RT is again R1 plus R2, so 20 ohms plus 60 ohms is equal to 80 ohms. So E is 64 volts and RT is 80 ohm. So the answer is 64 divided by 80. We have 0.8 amperes. That's the answer. Now here we have a parallel circuit question. We have to find RT. Now the formula for finding RT in parallel circuits is RT is equal to 1 over R1 plus 1 over R2. R3 doesn't have a value here. R3, let it be 5 ohms. So 1 over R1 plus 1 over R2 plus 1 over R3. And then enclose them in brackets and invert them to the power minus 1. So let's see what we have. We have 1 over 3 plus 1 over 4 plus 1 over 5 to the power minus 1. And that equals to 1 over 3 plus 1 over 4 plus 1 over 5 to the power minus 1. So that's 1.3. 1.3 ohm. Now notice an important thing. The smallest resistance in this circuit is 3 ohms, but the total resistance is 1.3 ohms. So this is another feature of parallel circuit, that the total resistance in a parallel circuit is always smaller than the smallest individual resistance. Okay, so 1.3 is the total is smallest than the smaller than the smallest individual resistance of 3 ohm, which is completely opposite to series, where in series the total here 80 is larger than the largest individual resistance, which is 60. Okay, so that's an easy way to verify that your total resistance is correct in parallel circuits, that you ensure that the total resistance is smaller than the smallest individual resistance. And again, that's our answer. Now, series parallel question. So a mixed circuit. Here we have R1 and R2. This 2 has a single common point, so it's a series circuit. And again, a series connection. And again, R3 and R4, again a single endpoint, so series connection. But R1 plus R2 and R3 plus R4 has 2 common points, so they're in a parallel connection. Again, whatever we have here, everything here is connected to R5 with 1 common connection, so it's a series connection. Now this for finding IT, we need IT is equal to E. We don't have a value of E here, so E would be say 60 volts. Okay, so 60. So IT would be IT is equal to E over RT. Now let's see. Let's simplify it individually. So here we have R1 and R2. So in series, let's do R1 and R2. That will be 3 plus 5 is equal to 8 ohms. Again, R3 and R4 is in series, so R3 plus R4 is equal to 1 plus 4. That is 5 ohms. Now R1 and R2 is in parallel with R3 and R4. So 8 and 5 are in parallel. So that would be, let's denote it as RP is equal to 1 over 8 plus 1 over 5 and then to the power minus 1. So that is 1 over 8 plus 1 over 5 to the power minus 1. 3.1. 3.1 ohms. Now this RP is in series connection with R5, the last remaining resistance. So this would be our RT. RT is equal to RP plus R5. So that is 3.1 plus R5 is 2. So that is 5.1 ohm. Now a total current, so IT would be IT is equal to E over RT. Now for E we had 60 volts. Here we had 60 volts and RT is 5.1 ohm. So 5.1 is equal to 60 over 5.1, that is 11.8. 11.8 amperes. That is our answer. Now let's move on to the last question. Now, this looks like a complex or complicated circuit. This is obviously a mixed circuit, series parallel. We have series connections and parallel connections, many of them. Now, when you have a complicated mixed circuit as such, an easy way to approach the problem is to start from the back. Don't start from here, but start from here, from the last resistor. Now the last resistor is 10 ohm. If we look closely, 10 ohm and 2 ohm has a single common point, right? So we can conclude that 10 and 2 are in series. Again, 10 plus 2 has 2 common points with this 1 ohm right here. So we can say those 2 are in series with 1 ohm. Again, that 1 ohm has 2 common points with 3 ohm. So we can say that 1 and 3 are also in parallel. So 10 and 2 are in series. Then 10 plus 2 is in parallel with 1, and then this 1 is in parallel with 3. So let's start with the series part. So we have 10 and 2. That would be, let's denote it as RS1. RS1 is equal to 10 plus 2. 10 plus 2 is equal to 12 ohms. Okay. Now let's calculate the parallel part. So this RS1 is in parallel with 1 and 3 because 2 common points. So RP, let's denote it as RP1. RP1 is equal to, wait a minute, if you look closely, this 1, 3 again is in parallel with 4 ohms. So here a common point, again common point, and again this 4 ohm is in parallel with 5 ohms. So common point, common point. So our RP1 will actually be RT. So let's change that to RT. Now RT is equal to, it's a parallel, right? So we can write 1 over RS1, again going from the back, plus we have 1 over 1. RS1, let's just write it as 12 ohms. So RS1 is 12 ohms, 1 over 12, plus we have 1 over 1, so just 1, and then we have 1 over 3 plus 1 over 4 plus 1 over 5, and then we enclose it in brackets and to the power minus 1. And let's put that in the calculator. So 1 over 12 plus 1 plus 1 over 3 plus 1 over 4 plus 1 over 5 to the power minus 1, and that equals to 0.54. So 0.54 ohms. Now we have to find IT. Again, IT, simply Ohm's law. So E over RT, that is, what is E? E is 30 volts here. So 30 volts over RT, which is 0.54 ohms. So 0.54. And that equals to 30 over 0.54, 55.56. 55.56 ampere. That is our answer.